Hello, everyone. Welcome to another class of computational thinking, in which we will discuss about logical thinking. Okay, let me get started. In this class, the aim of this class will be to learn how to apply logic to problem solving. And some of the concepts that we will use for this purpose will be valid argument, deductive and inductive reasoning, Boolean logic, and logical operators. We will go over all these concepts one by one throughout this class. Okay, let's get started. So let's first talk about the definition of a starting definition of logic. Logic is a system of thinking used to distinguish between valid and invalid arguments for deductive logic or strong and weak arguments for inductive logic. And now here I'm introducing new concepts in order to describe one concept, in order to define one concept, and we will go over all these definitions again one by one. So why are we learning these logical operators or these logical methods in a computational thinking class? One of the reasons is because computers automate human reasoning. We need logically valid or strong reasoning before we can command computers what to do. They are just imitating our reasoning, and of course they're using it more efficiently, but that's the starting point also for computers. So that's why we have to understand how to build logically valid or strong reasoning before we can command computers to do anything at all. So what do I mean by a valid argument? Here is a very famous example coming from ancient Greek philosopher Aristotle. On the right-hand side of the slide, you see a picture of Aristotle's, which is a modified picture. Of course, he didn't have a Mac in his time. In this picture, you can see him with his Mac teaching his students. And here on the left-hand side, you see a famous example of a valid argument that Aristotle proposed. Here is how the argument reads. There is premise one. You can also think of it as a statement one. All humans are mortal. This is a true statement. It's a true premise. Premise two, Socrates is a human. Socrates is another ancient Greek philosopher. The second premise says Socrates is a human, which is also a true premise. And the conclusion that stems from these two premises says Socrates is mortal, which is also a true premise. So this is a valid argument. This is the most famous valid argument coming from Aristotle. In a valid argument, there is no way for the conclusion to be false as long as the premises are true. So what do I mean by this statement? Look at, again, this valid argument. There are two premises, which you can also think of as statements that we use to reach a conclusion. Premises are statements that we use to reach a certain conclusion. And one conclusion here, this is a very simple logical statement, valid logical statement. The first two premises are true in this statement. So in a valid argument, there is no way for the conclusion to be false as long as the first two or more statements or premises are true. So again, in this valid argument, there is no way for the conclusion to be false as long as the premises are true. That's why this argument is a valid argument. Some arguments might give false conclusions because they involve invalid reasoning. So, as I said, in a valid argument, there is no way for the conclusion to be false as long as the premises are true. But in an invalid argument, on the other hand, when the premises are true, even when the premises are true, we might reach a false conclusion. That shows that there is a problem with our reasoning. Our reasoning in such an argument is false. And technically, we call it invalid reasoning. Here, look at this example. Premise one, all humans are mortal, which is a true premise. Premise two, Roxy the cat is mortal, which is also a true premise. We know that cats are mortal. Conclusion, Roxy the cat is a human. And this is a false conclusion. Roxy the cat is not a human, it's a cat. And the reason why we could have a false conclusion, even when we had true premises, is because the reasoning is mistaken. There's a mistake in our reasoning here, and we call such mistakes under the heading invalid reasoning. Whether an argument is valid or not depends on its form. Here comes another technical term, form. There are rules of logic that we use to find out whether the form of an argument is valid or not. And we cannot cover all these rules in this class, but I will give you just one such example. Look at this form. Forms include these parameters, as you can see on the left-hand side, bottom corner of the left-hand side. Here you see the parameters x and y and the small case letter a as the constant, and we have converted the valid argument on the top left corner into almost a ciphered sentence, all x are y, a is x, therefore a is y. So I replaced human mortal Socrates in the previous argument with x, y, and a, and I reached the form. So the reason why the argument on the top left is valid is because the form that's shown in the bottom left is valid. And I mean, as introductory, as being in an introductory class for computational thinking, you don't have to know which forms are valid and which forms are not valid. I'm just giving you one example of a valid argument form. You just need to understand that an argument is valid as long as its form is valid, and form is something that you reach when you remove all the parameters or constants from an argument and replace them with variables like x and y and constants like small case letters A's, B's, and C's. That's what that form is. That should be your takeaway from these couple of slides. Okay, let me go ahead. Now think of a simple robot called Stonehat. We teach Stonehat this valid form and ask it to give us true conclusions. Let me just repeat this part. If you use a valid form, valid argument form, there is no way that you can reach a false conclusion as long as you feed the computer with true premises. And that's what we will do with Stonehat. We teach Stonehat to use this valid argument and to understand human sentences and give certain premises and ask the Stonehat to give us true conclusions. We feed Stonehat with this information. Premise 1, all cats are white. This is the false premise. We feed Stonehat with a false premise on purpose to show you some results. And premise 2 is Roxy is a cat, which is a true premise. And this is what the Stonehat will return to us using the valid form that we had touted. The conclusion is Roxy is white. And this information is false because I know that Roxy used to be my cat actually when I was living in the United States. And this is a picture of Roxy. And you know that we all know that Roxy is a black cat. So the conclusion is false. And although the form was valid, the conclusion is false because we fed the computer with false information, with false premise. The form of this argument is the same as the form of the previous one. It's a valid form. The difference is the truth value of premise 1. It's simply false in this argument. If we want to get true results from a computer, we need to feed true information. I know that this is a very simple example, but I will go into more difficult examples, more complicated examples, but I want you to understand the idea behind how you can, the idea behind one of the reasons how you can reach a false conclusion, although you have a valid argument. And again, the reason is you might be feeding the computer with false information. That's one of the reasons why you need a false conclusion course. Now take this example. You want to use Stonehat to help police force to make decisions. We program Stonehat with the valid argument from the previous slide and the ability to convert suitable plain sentences to this form. Then we feed Stonehat with this information. Premise 1, all black people are under suspicion for some crime. Premise 2, this person approaching the police car is a black person. And we ask Stonehat, is she under suspicion for some crime? Of course, Stonehat's answer will be, this person approaching the police car is under suspicion for some crime. So the person gets arrested, etc. What went wrong here? We need to check the information we feed to the computer. And for this purpose, we need critical thinking skills, which we will learn in the coming class. So again, this is a very, very simple example. This is a completely simplified example of what's actually going on in real life. Computers, we trust computers to take decisions or to help us take decisions, actually, not necessarily always take decisions, but to help us take decisions. We use computers in police force, we use computers in banking system, we use computers in university entrance systems, we use them everywhere. And we use them for helping us taking decisions. The decision of the computer, although we feed it with the right argumentation forms, might be wrong because we might be feeding it with false information. This is one of the reasons why you might reach false conclusions. Okay, let's go deeper into this discussion. So first, we have to divide logic into two different divisions, two different types: deductive reasoning and inductive reasoning, or we can also call them deductive logic and inductive logic. Deductive reasoning or deductive logic deals with the form of an argument, as I have shown you before. It's like a ciphered form, ciphered version of an argument, like x, all x are y, a is an x, therefore a is y, etc. This is a form of an argument. Deductive reasoning deals with a form of the argument. It deals with this question: would the conclusion of this argument be true if all of its premises were also true? In a valid argument, as I said before, there is no way for the conclusion to be false as long as the premises are true. Deductive reasoning may or may not give us true conclusions. The truth value of conclusion depends on the truth value of premises, as we have seen in the example of Proxy the cat. Now take the premises above. First premise, all humans are mortal. Second premise, Socrates is a human. And conclusion, Socrates is mortal. The example that I gave a couple of slides before. Here, Socrates is mortal is true if both premises 1 and 2 are true. This is what I've been saying. This was about deductive logic. Now we come to inductive logic. Inductive logic or inductive reasoning uses the idea of observation and experiment to reach more or less probable results. Deductive reasoning was reaching certain results. That's how deductive reasoning or deductive logic works. Whereas inductive reasoning takes us to probable results, more or less probable results. Inductive reasoning does not always give certain results the way deductive reasoning gives. And where do we use the inductive reasoning? We use it in all of the scientific inquiries we exercise today. Contemporary science uses inductive besides deductive reasoning. So we do not do away with deductive reasoning. We still use it, but in order to reach scientific results, we need inductive reasoning, inductive logic. Take again the premises above. All humans are mortal. Socrates is a human, and Socrates is mortal. This was the typical example of deductive logic that I gave before. Socrates is mortal is true if both premises 1 and true. As I was saying, this is the attribute of a valid argument. Finding the truth value of all humans are mortal requires a specific way of reasoning, which is inductive logic. In this case, all humans are mortal requires scientific observation and explanation. Of course, this is a very simplistic example for all of us, right? I mean, we do not necessarily need scientists and laboratories to reach the conclusion that all humans are mortal. But take this example as a simple example that explains how all other more difficult examples work. If you are getting a scientific result, you need inductive reasoning. And then you can use that inductive reasoning, and then you can use that result that used by means of inductive reasoning to, in a deductive logical form, to reach different conclusions. And I'm trying to show you that you need both inductive and deductive reasoning to reach conclusions, either scientific or non-scientific, of any sort. Take another example. Each of the 2 times I ate broccoli, I got sick. Therefore, I'm probably allergic to broccoli. So here, the premise is each of the 2 times I ate broccoli, I got sick, and the conclusion is therefore I'm probably allergic to broccoli. This seems like an inductive logic because the result is intended to be a probable result. The result is not meant to be a certain result like in deductive reasoning. The person who makes the argument, in this case it's me, is intending to give a probable result here. But we still have to understand whether the result is backed up strongly or weakly by the premises that are given here. And in this case, it's a weak inductive reasoning that requires more observation or scientific experiments to be accepted as true. As you can see, you cannot rely on just 2 cases of eating broccoli to reach the conclusion that you're allergic to broccoli. You need more experiments. You probably need some allergy tests, etc., to reach that conclusion. So I'm trying to show you that inductive reasoning can be weak or strong. This one, the example on the screen that you are seeing now, is a weak inductive reasoning. The scientific results that we reach through thousands of experiments are benefiting from strong inductive reasoning. Why are they strong? Why are they benefiting from strong inductive reasoning? And this example on the screen is just an example of weak inductive reasoning. It depends on how probable the result is backed up by the premises given in the reasoning. So compare a scientific experiment versus my observations on my body after eating broccoli just 2 times in my life. And you can see that this is why you can see why this is a weak inductive reasoning. Okay, let me just go over some of the terminology that I have explained until now. So first of all, we have an argument. An argument is a collection of statements, as you have seen in our examples, like premises, intended to support or infer a claim, which is a conclusion. Each statement has a truth value of either true or false. This is what we call an argument. An argument can be classified as deductive or inductive. And how do we classify them as deductive or inductive? We have to look at more or less the intentions of the person who is making the argument. If a scientist is making an argument, intending it to be a scientific argument, then we have to take it as an inductive argument. If somebody is like trying to reach a certain conclusion, if that's their intention, we have to take it as a deductive argument. Again, deductive arguments can be valid or invalid, as you can see in the third column of this schema. And determining validity and strength requires further investigation on the argument, right? If we assume the premises are true, then does the conclusion follow? That's the test for valid arguments. Inductive arguments can be strong or weak, as in our example of scientific inquiry versus me observing my body after eating broccoli just 2 times. That was a weak example of inductive argument, right? We further, on the 4th column on the slide on the screen, you can see that we further divide valid, invalid, strong, and weak arguments into 2 separate groups. Valid arguments can be sound or unsound. Invalid arguments are necessarily unsound. Strong arguments can be cogent or uncogent, depending on how strong they are. This is not our concern for the time being. These are just a schema for showing you how we can classify arguments. Let me just go a bit further. So now I would like to talk about Boolean logic. Boolean logic is a logical system that uses propositions and some logical rules to reach conclusions. It was created by the mathematician George Boole, and I will show you in a second a short video about George Boole. But the idea here is we started with ancient Greek philosopher Aristotle. Aristotle gave us the rules of deductive logic like centuries ago. And we are still using some of those rules and we are building upon it. And this British mathematician, George Boole, benefited from the deductive logic rules that Aristotle gave and took that logic to a very high level. And from this slide on, I will talk about how George Boole benefited from Aristotle's deductive logic to all those simple examples that I've given you in the previous slides and took us to a point where we can build computers that we are using today that I'm making this presentation on right now. Okay, let me just show you first this short video to introduce you with George Boole, the person. Okay, apparently George Boole made a revolutionary discovery. And as the video says, that discovery keeps on changing our world. So, okay, let's talk about that discovery.
Today, everything relies on math.
So the discovery that George Boole made regards how we can use logic that stems from ancient Greek philosopher Aristotle and benefit from that logic to reach all these computer systems. And how did Boole reach that conclusion? It's a very interesting process that's going on here. So from this slide on, until the end of today's class, I will talk about Boolean logic. And as you can see, the word Boolean in Boolean logic comes from George Boole, whose video you have just seen. So, excuse me. So Boolean logic stems from Aristotelian logic, this deductive reasoning that I've just shown you a couple of slides before, and builds on it to reach this complicated system, which we can benefit from to build our computers. Okay, how is this happening? how can we start from that very simple idea of a deductive logic? All men are mortal, Socrates is a man, therefore Socrates is mortal. That's valid form. How we can start from that form, that very simple form, and reach today's computers. What's going on here? Okay, let's move on and see how that step was taken. So first, I will talk about a couple of concepts that we use in order to understand Boolean logic: propositions and logical operators. Let me start with propositions. Propositions that Boolean logic can use are either true or false. They cannot be somewhere in between. This is our first rule about propositions, okay? From this slide on, we are talking about Boolean logic. We will understand how George Boole benefited from Aristotle's deductive logic and used that idea to build a theory, to build a system that we lean on to make our computers that we use today, okay? And two concepts that we use in order to understand Boolean logic are propositions and logical operators. Now I will talk about those two concepts. I start with propositions. To repeat myself, propositions that Boolean logic use are either true or false. They cannot be somewhere in between. And I have got 4 examples on this slide on the left-hand side. Mount Everest is the highest mountain in the world. This proposition is a true proposition. I give you a sentence. A proposition is a sentence in any language. So in this case, we use English language to build our propositions. I say Mount Everest is the highest mountain in the world. It's a true proposition. So this proposition can be a proper proposition to be used in Boolean logic because it has a truth value. It's either true or false. Look at the second proposition or the second sentence. Mount Fuji is the highest mountain in the world. And on the right-hand side, you see the pictures of these mountains. And this is a false proposition. You can check your Google or any other search engine to see that Mount Everest is the highest mountain in the world and Mount Fuji is not the highest mountain in the world. This is a false proposition. But being a false proposition means that it has a truth value. Truth value means something is either true or false. So we can use this second sentence in a Boolean logical argument as well. It's enough for us for a proposition to be true or false to be used in an argument that we use Boolean logic in. Okay, look at the third one. Is Mount Everest the highest mountain in the world? This is a question. It doesn't have a truth value. The answer of this question has a truth value. You either say yes or no, and depending on your answer, your answer will be either true or false. But this question itself does not have a truth value. The question is not true or false. The answer of it will be either true or false, okay? So questions are not propositions. We cannot use a question in our Boolean logical arguments. And the fourth one says, climb Mount Everest. It's a command, it's an imperative. And imperatives or commands are not propositions either. It doesn't have a truth value. The action that you take depending on this, or the answer or the response you give or the action you take after this imperative might have true or false value. You might say, no, I'm not going to climb, and which might have a true value. But the imperative itself does not have a truth value. So here in this slide, I'm trying to show you that propositions which have either true or false value can be used in our arguments when we are dealing with Boolean logic. Okay, let me go on. Second attribute of propositions. Propositions cannot be ambiguous. Their meaning must be clear, okay? Look at this example. And this is a beautiful picture of Mount Erciyes, by the way, on the right-hand side. Look at this example, look at this proposition. Mount Erciyes is very high. This is not a proposition unless we define what we mean by high in this context. High might mean something for me, it might mean something else for each one of you guys, right? So if you want this sentence to be a proposition, either in a separate proposition or within the same proposition, we have to define by high, I mean any mountain that's higher than 4,000 meters, for instance. We have to define it. Otherwise, ambiguous sentences cannot be propositions that we can use in Boolean logic. Okay, we go on. A third attribute of propositions. Propositions can be connected together to make compound propositions using logical operators. Oh, sorry. Let me just read it again. Propositions can be connected together to make compound propositions using logical operators. And here are 2 examples. Mount Everest is the highest mountain in the world, and I used to have a cat named Roxy. This is a true compound proposition. Again, what makes this a compound proposition and not a simple proposition? Using the operator and in the middle of the sentence, as you see here, I combined two simple propositions. The first simple proposition is this: Mount Everest is the highest mountain in the world. And the second simple proposition is this: I used to have a cat named Roxy. By using the operator and, I combined these two sentences. Since both are true propositions, the compound proposition is also true. I will say more on this in the coming slides. Look at the second example. Mount Everest is the highest mountain in the world, or we are in August. This is also a true compound proposition. The first simple proposition is this: Mount Everest is the highest mountain in the world. It's a true proposition. The second simple proposition is this: we are in August. It's a false simple proposition. A true simple proposition and a false simple proposition combined with the or operator makes a true compound proposition. Why does it make a true compound proposition? Will be explained in the coming slides, so don't worry yet. Okay, let me go on. Now let me come to logical operators. In the previous 3 slides, I gave you some attributes of propositions. I gave you 3 attributes of propositions. They cannot be ambiguous. They should have either true or false value, and they can be connected using operators. In the third attribute, I mentioned logical operators. So now I have to explain what I mean by logical operators. Propositions can be connected using logical operators to form compound propositions. And some of the logical operators that we will learn in this class hour are these: and, or, not operators. Okay, and here are some alternative names that are used in the literature. We say for and operator, we also say conjunction operator. For the or operator, we also say disjunction operator. And for the not operator, we also name it negation operator. Here is how we can use the and operator, the conjunction operator. This is the conjunction operator, and the compound proposition is true only if the propositions making up the compound are both true. Look at the example. Mount Everest is the highest mountain in the world, and I used to have a cat named Roxy. This is a true compound proposition because both of the propositions are true. We know that Mount Everest is the highest mountain in the world. We trust observations and scientific findings. And we know that I used to have a cat named Roxy. You have to trust me for the truth value of this proposition. I assure you that I had a cat named Roxy, and here is the picture of this cat. So this is a true compound proposition because two propositions that are connected together using the and operator in the middle are both true. Okay, look at the second example. Mount Everest is the highest mountain in the world, and I have blue hair. So the first part of this compound proposition is true. It's true that Mount Everest is the highest mountain in the world, but the second part is false. I do not, as you can see, have blue hair, or as you can see in the picture, I'm not that person who has the blue hair. So this compound proposition is false because it doesn't fulfill the condition at the top left of this slide. We need both of the propositions that are connected by and to be true. Here we have only one of them true, that Mount Everest is the highest mountain in the world. I don't have blue hair, so this compound proposition is not true. Okay. Here is what we call a truth table. Okay, this is the truth table for the and operator. And here is how we fill this truth table. At the top row, I write PQ, P and Q on the right-hand side. P stands for the first proposition that we use in a compound proposition that is connected by and. In this case, for instance, look at the first example on the left-hand side. Mount Everest is the highest mountain in the world, and I used to have a cat named Roxy. P stands for Mount Everest is the highest mountain in the world. In this example, P stands for the first part of that compound sentence that you can see before the operator and. Q stands for the right-hand side of the and. I used to have a cat named Roxy. And the truth table gives us how P and Q, the value of P and Q turns out to be depending on the values of P and Q. Okay, so when P is, look at the first line here. actually it's the second row after PQ, P, and Q row, the second row on the screen, which I think I can use some pointers here. I'll use a pointer, laser pointer. Okay, let's look at this row. Look at this row here. When P is false, when truth value of proposition P is false, and when the truth value of proposition Q is false, the truth value of P and Q is also false. This is how you should read this truth table. Okay, look at the second row here. When P is false, Q is true, P and Q is also false. When P is true, Q is false, P and Q is still false. P and Q is true only when both of these propositions are true, like in this example. In this example here, both of the propositions are true, hence P and Q is true. And look at this example. Mount Everest is the highest mountain in the world, which is P in our case, and it's true. And I have blue here. This is false. This stands for Q, and it's false. We have true for P and false for Q, which makes P and Q false. So we are given these truth tables. We know how these truth tables are formed. You are not supposed to come up with these truth tables. Aristotle gave us these truth tables, and we are just benefiting from it. And George Boole is also benefiting from these truth tables to reach his theory about how we can build computers using these Aristotelian theories. Okay, this was the truth table for operator AND. Let me come to operator OR, the disjunction operator. In this case, the compound proposition is true if at least one of the propositions making up the compound is true. Look at the examples. Mount Everest is the highest mountain in the world, or we are in August. It's enough for one of the propositions that make up the compound proposition to be true for the compound proposition to be true, okay? So this, where's my laser pointer? Okay, here is my pointer. This compound proposition is true because the first part, P, Mount Everest is the highest mountain in the world, which stands for P, is true. We are in August is false. We are not in August, but we have a true P. I look at my truth table for OR. This time I'm looking at the truth table for OR. This is a different truth table compared with the previous truth table. You can go back in the video and see that the truth tables are different. Here, this time, for this example, the first example on the left-hand side, we have true for P, Mount Everest is the highest mountain in the world, is true. And we have false for Q, we are in August is false. But even then, P or Q is true. Again, this truth table is given to us. We know that this is the truth table for the OR operator, okay? We look at the truth table and find out how P or Q comes out. Look at the other example. Mount Fuji is the highest mountain in the world, or we are in August. The first part is false. Mount Fuji is not the highest mountain in the world. P is false. So I go to this truth table and I find where P is false. In the first two rows, P is false. Now let me see if Q is true or false. We are in August. We are not in August, so Q is false as well. P is false. Q is false. This is the only line where P and Q are both false. So I look at the right-hand side of this line and see that P or Q, the value of compound proposition, P or Q is also false. I understand that P or Q is false looking at this truth table. Okay. This is how we read truth table for the OR operator. Okay, until this point, I have talked about two logical operators, AND, OR. And I have given you truth tables for these operators, and I've tried to show you how to read these truth tables and find out whether the truth value of the compound proposition is true or false looking at the truth table. Let me now move on to come to our next operator, our last logical operator, NOT. This is the negation operator. The truth value of the compound is the opposite of the truth value of the proposition that the operator is applied to. Let's look at the examples. The sentence might be a bit complicated, but let's look at the examples to understand what's explained in the sentence. And the truth table, as you can see, is very simple here because we don't have Q here. Not, the operator not is applied to only one proposition. In the previous truth tables, you will remember that both and OR are applied to two propositions, P and Q, P or Q. Here you apply not to only one proposition, not P, not Q, or not Y, not Z, whatever. So, okay, let me just read these examples here. Look at the first example. It's not the case that Mount Fuji is the highest mountain in the world. Please see that instead of only saying not, I say it's not the case that, because it fits better in the English language. I could also say not Mount Fuji is the highest mountain in the world, but it wouldn't make a meaningful English sentence. So that's how I convert the operator not into English sentence here. I say it's not the case that. It's not the case that Mount Fuji is the highest mountain in the world. So in order to understand whether this sentence is true or false, I separate it's not the case that as an operator from the rest of this sentence, and the rest of the sentence I call P. Mount Fuji is the highest mountain in the world. It's false. I know that it's false because science tells me that it's false. I look at the truth table where P is false, and I see that not P is true. So when P is false, not P is true. When P is true, not P is false. Not surprising, right? I know that these examples are really simple examples, but really simple examples make us understand how this system works, how we read truth tables, and then we can move on to more complicated examples. Actually, we can even move into very complicated computer chip and understand how the chip works just by taking a couple of steps further than these very simplistic examples. So please bear with me, try to understand how these simple examples work, and you will get to more complicated ones in a bit. Look at this second example. It's not the case that, and I use the parentheses here not to complicate the issue any further, to make it easy to understand, and to make it easy to read. It's not the case that Mount Fuji is the highest mountain in the world, or we are in August. Okay, now things are getting a bit complicated. Just look at what's happening within the parentheses. Ignore for the time being, it's not the case that. Just look at this compound proposition within the parentheses. Mount Fuji is the highest mountain in the world, false, or we are in August, false, false or false. Let me go one slide back to the truth table of or. Okay, when P is false here and Q is false here, P or Q is false. Let me move forward again. Here in this example, looking at the proposition within the parentheses, we have false or false. I went back, looked at the truth table for or, and I saw that false or false gives a false result. When P is false and Q is false, P or Q is also false. Okay, so within the parentheses, we have a false value. It's not the case that a false sentence. So here, whatever is in the parentheses becomes P for me. Here, look at here. Whenever P is false, not P is true. So the proposition within the parentheses has false value. When I add, it's not the case that to its beginning, the total value becomes true. How do I understand it? Looking at the truth table for not operator. When P is false, not P is true. Like immediately you might ask this question, okay, within the parentheses, P was standing for Mount Fuji is the highest mountain in the world. Now you call the whole sentence in the parentheses P. Okay, that might be complicating if you have never dealt with variables, etc., or if you forgot your polynomials that you learned in your high school education. But these are variables, P and Q. So you can replace P and Q with all sorts of propositions. When I was dealing with the proposition within the parentheses, the first sentence before or, which is Mount Fuji is the highest mountain in the world, was P. When I'm done with the whole parentheses, then I can call the whole parentheses P, because P is a variable, and variables, like as the name suggests, vary. The value of the variables change. Okay, I'm not 100% sure that many of you will be confused by this, but just wanted to make this clear. Okay, let me move on to the next example. Again, it's not the case that, open parentheses, Mount Everest is the highest mountain in the world, and operator, and I have blue hair. Mount Everest is the highest mountain in the world, true, and I have blue hair, false. What's the truth value of true and false? Let me go back 2 slides now to the truth table of and. So Mount Everest is the highest mountain in the world, true. So P is true. Where's my pointer? P is true, and I have blue here, false, Q is false. So we have true and false. True and false gives a false result. Let me go forward 2 slides. Here we are discussing this example. Within the parentheses here, Mount Everest is the highest mountain in the world, and I have blue here, gives out false result. True and false gives out false result. So in the whole sentence here, it's not the case that a false sentence. Here, whatever is in the parentheses can be named P, can be represented by the variable P. So it's not the case that P, where P is false. Again, when P is false, not P is true. Okay, that's why the whole value of this sentence is true. Okay, in the last 2 examples, I try to show you how and or not can be used together to make like compound sentences and how to make their truth values, like first dividing the compound sentences into simpler compound sentences and then looking at the truth tables to find the truth value of these simple compound sentences and then going back up to the more complicated, more compound sentence or proposition to find the truth value of the whole thing that we are investigating. Okay, let me just move on. If you have digested all this, let me just move on further into the depths of Boolean logic. So now we turn all this that we have learned about like truth tables, truth values, and or not operators into computer language. We replace, in order to convert everything into computer language, we replace true with 1 and false with 0 in our truth tables. In our truth tables, this is the exact same truth table for AND operator that you can find in 3 slides back. If you don't believe me, just go back 3 slides back and check it out. I just replaced F with 0 and T with 1. And when I did that, I reached this truth table for P and Q, where T and F are replaced with 0 and 1. And this is the truth tables for all these 3 operators. On the left-hand side, you'll see the truth table for AND with 0s and 1s as values. In the middle, you see the truth table for OR, again with 0s and 1s as values. On the right-hand side, you'll see the truth table for NOT operator. I just replaced T's with 1s and F's with 0s. There's nothing else that I've done until this point. Okay, let me move on and try to explain why I did change T's with 1s and F's with 0s and how this change will turn these Aristotelian truth tables into a computer language that George Boole is famous for. Okay, now I will show you another video.
Inside your computer are billions of units called transistors. These transistors serve a variety of purposes, but they commonly act as a sort of very small light switch. Each switch can be turned on or turned off. Computer scientists will often represent a switch that's turned on with the number 1 and a switch that's turned off with the number 0. These 0s and 1s form a number system called binary, and it's the fundamental language of computers. From just these 0s and 1s, we end up with computers that can perform calculations, create documents, view images, browse the web, and more. How does that happen? In this series, we'll explore the foundations of computer logic, starting from the fundamentals and building our way to more and more sophisticated systems. Using these switches, our computers can store information. Each switch stores a single bit of information, a 0 or a 1. But computers don't just store information, they process it, transforming inputs into outputs. That's where logic gates come in. Logic gates are the building blocks of computer circuits. They accept input and produce output according to a set of logical rules. One of the simplest logic gates is the NOT gate, represented graphically here. The NOT gate takes a single input, either a 0 or a 1, and inverts it so that the output is the opposite of whatever the input is. If the input is a 1, then the NOT gate outputs a 0. If the input is a 0, then the NOT gate outputs a 1. to represent the logical rule this gate obeys, we can draw a truth table, which is just a way of writing down the rules for some logical formula. This table says that if the input is 0, then the output is 1, and if the input is 1, the output is 0. Often, though, our computers need to be able to perform calculations not just on a single bit of information, but on multiple bits of information. The AND gate, shown here for example, is a logic gate that takes 2 inputs instead of 1. Let's call these 2 inputs A and B. As the name might suggest, the AND gate will output a 1 when both A and B are 1s, but in all other cases, AND will output a 0. We can construct a truth table here too. This truth table is a bit bigger, since with 2 inputs there are more possibilities to consider. If A and B are 0, the output is 0. If A is 0 and B is 1, the output is 0. If A is 1 and B is 0, the output is still 0, and only when both A and B are 1s is the output a 1. The OR gate, meanwhile, is also a logic gate that takes 2 inputs. This gate outputs a 1 when A is a 1, or when B is a 1. So if both inputs are 0, the OR gate outputs a 0. But if either of the inputs is a 1, or both inputs are a 1, then the output of the OR gate is also going to be a 1. These logic gates on their own follow fairly simple rules, but they can combine with each other to form more complex calculations. Imagine what would happen if, for example, we took 2 inputs, passed them into an AND gate, and then passed that output into a NOT gate. What would happen? If both inputs are 0, the AND gate will output a 0, and the NOT will turn that 0 into a 1. If only one of the inputs is a 0, nothing changes. But if both inputs are 1, the AND gate will output a 1, and the NOT will turn that 1 into a 0. In other words, this circuit appears to do the opposite of whatever the AND gate on its own would do. It turns out that inverting the result of an AND calculation is such a common operation that it has its own...
Okay, I think we can stop at this point. I mean, this video, I think, is nicely explaining what we have gone through until now. Yeah, as I was saying, this video is nicely summarizing what we have gone through until this point to explain how these AND or NOT gates function and how we can use these numbers, zeros and ones, to convert these into different numbers when these are connected together by these gates. Okay, so sorry. Yeah. We benefit from these logical operators when we are giving commands to computers. These logical operators are what we are benefiting from when we are giving commands to computers. We use logical gates, as you have seen in the video, to create circuits where the actual commands are carried by electrical signals. I started with sentences like Mount Fuji is the highest mountain in the world, I have blue here, etc. I try to show you how those propositions can be combined together to make compound propositions and even further compound propositions, adding other operators. And then I try to show you how you can replace truth values with ones and zeros, and how you can combine those ones and zeros by a computer logical unit called gate. That's the technical term that you have seen in the video. All these shapes were gates. And those gates make up these circuits that we use within computers. Here again, we can see the symbols that are showing logical gates on a circuit. You'll see on the top AND gate, OR gate, NOT gate, and on the bottom you see a rather complicated circuit. It's a simple circuit compared to actual circuits, but for our purposes, it's a rather complicated circuit using multiple gates together. When a certain switch is turned on, like the switch on your wall, I mean, when you turn on the switch, your lights are on. When a certain switch is turned on, the gate interprets this action of turning the switch as on as 1. And when the switch is turned off, the gate interprets it as 0. So this is the logic behind how we can use all these truth tables that include zeros and ones and reach conclusions. When a certain switch, and on the picture you see letters A, B, and C, you can imagine them as switches, like as light switches. You can either turn them on or off. When, for instance, A is on, when A light switch is on, you can think of it as a 1 in our logical operation. So a number 1 is going into, where's my laser pointer? Oh, okay. Just make the full screen again. Oops. Look at here. When you switch this A switch on, you can think of as number 1 is traveling through this wire and coming to a NOT gate, and the NOT gate converts or inverts 1 into 0, and a 0 is going on through this circuit and coming to this AND gate. Okay, this is what we can imagine happening here. When a certain switch is turned on, the gate interprets it as 1, and when the switch is turned off, the gate interprets it as 0. Then the gate makes a logical operation and gives out one output. The logical calculation that comes out of all gates is given out as the output of the whole circuit. So if A is 1, if switch A is on, you can take it as a 1. Number 1 is traveling through this wire, coming here, getting out as a 0 because it's a NOT gate, and coming to this AND gate as a 0. And you can just play with the numbers for B and C gates and find out what the output will be. Let me just show you a truth table here for a rather simple circuit. Look at here. We have A switch, B switch, a NOT operator, or a NOT gate rather than operator, a NOT gate connected to A switch, a NOT gate again connected to a B switch, and we use an OR gate here. Look at the previous slide. You differentiate between OR and AND gates looking at their bottom side. If it's a straight bottom, it's an AND gate. If it's a bottom in the shape of an arc, then it's an OR gate. OR gate has a sharper tip in this picture, and it doesn't have a sharper tip in this picture. You can use both, but the end of it shows whether it's an OR gate or an AND gate. AND gates have a, go back one slide again. AND gates, as you can see at the top, have a straight end. OR gates have a tilted end or an arc-shaped end. Here in this picture, we have 2 NOT gates here and 1 OR gate. Here is the truth table for this circuit. We have A, B, not A, not B, and Y, which is the result of combining these 2 numbers and putting into an OR gate. So how do we use this truth table? Here is an example. Take just this line. What's happening in this line? A is 1 and B is 0. What does this mean in terms of computer circuit? It means switch A is turned on. That's what 1 being 1 in a computer circuit means. And switch B is turned off. That's why it's a 0. For this line, switch A is 1 and switch B is 0. When switch A is 1, we know that looking at one of our previous tables about the NOT operator, we know that when A is 1, not A is 0. So this column is for not A value, not A is 0. And I know that when B is 0, here, look at this line. When B is 0, not B is 1. So now in order to find out the value of Y on this circuit, the value of Y, here from A, we had 1. This NOT gate turned it into a 0. So a 0 transferred through this wire and a 0 came to this point where my laser pointer lies. Here B was 0, NOT gate turned it into a 1, and a 1 is coming here. So here we have, at this point we have a 0, and at this point we have a 1. We have an OR gate here. OR gate takes a 0 and a 1. What does an OR gate give out? How should we know? We can just go back a couple of slides and look at the logical table for OR, which is in the middle. When P is, in our example, it was A's and B's. In this table is P and Q. That doesn't make any difference for us. These are just variables. So the first one is, what was our values? What were our values? The first one is a 1 and the second one is a 0, right? When the first, let me just make sure that's our values. Those are our values. In our example, sorry, our values are, the first one is a 0 and the second one is a 1. Okay, these are our values. Let me go back a couple of slides now. The first one is a 0 and the second one is a 1. P or Q, we have an OR gate there, P or Q returns a 1. Let me go forward here. So when the first one is a 0 and the second one is a 1, P or Q returns a 1. So the last column here, this column, is empty at the beginning. We fill it. So the last column is not given by our truth tables that were in the previous slides, okay? We have only 3 truth tables that I showed you just a second ago. A truth table for AND, a truth table for OR, and a truth table for NOT. When we are given a circuit like this, we can find the value of Y as long as we are given the values of A and B. A is, in this example, A is 1. We are given that A is 1. We are given that B is 0. We are not given anything else. And we are asked the truth value or the numerical value, the Boolean value of Y. We are given A, we are given B. We are not given anything else. We are given the circuit. And the question asks us the truth table of Y. In such a case, we can just use the 3 truth tables in our previous slides to come up with this result. I looked at the previous truth table for NOT to find this value and this value. I went back and looked at the truth table for OR. Why did I look at the truth table for OR? Because here we have an OR gate. And I found the truth value for Y. Which means if there were a light bulb at the end of this circuit, which is Y, it would be on. The light bulb would be on. Okay. You can play with these circuits in this website, and actually that's what you will be doing in the lab session. You will be going into this website, and I'll be giving you, and the assistants will be giving you actually some questions written in logical form, and you will be asked to convert those logical forms into circuits like this one. And it will be very simple because you will use just 5 components. Switches, as you can see in the picture, these are switches. A, B, and C are switches. AND gate, switches. AND gate, OR gate, NOT gate, and a light bulb at the end. As you can see here, Y is a light bulb. You will use just these 5 components and create these very simple, elegant, beautiful looking circuits. And on the website, you will be able to play with these switches. You can just turn A on and off, B, you can turn B on and off, etc., and see whether the light bulb is lighting up or not. Okay, and this is actually, as you might remember from the video that I showed you, this is a very simple idea here. When a switch is on, it's 1. When a switch is off, it's 0. And just with this simple idea, we can build very complicated circuits that we use in our computers today. It's an incredible idea. And we owe this idea to George Boole. Of course, we owe what George Boole developed on to Aristotle, the ancient Greek philosopher Aristotle. As you can see, Aristotle lived in like between 400 and 300 BC, so many years ago. And he built all these basic rules for logic. And George Boole, this British mathematician, just took that idea and converted it into a numerical, calculable version that we call Boolean logic. And we can use that idea, that theory, to build very complicated computers today. And when we come to artificial intelligence, that idea can take us to all sorts of imaginary places. And we will talk about some of those imaginary places that this idea can take us in our next class. So this is the end of today's class. Thank you for bearing with me.